Moving on, really sort of moving on, exponential functions and logarithms. I got a kick out of this joke, but logarithms are really a different way of writing an exponential function. Um, Sort of. I'll show you. It fills a whole bunch of different holes in what we're doing. It allows us to solve a lot of different problems. So, what is a logarithm? If you've worked with logarithms already, I'm hoping you're not groaning. They're really, really useful. And once you get the hang of them, how to work with them, they can allow you to solve lots more problems than you could without. So this is what a logarithm is. Not this. This is an exponential function. So an exponential equation, y equals b to the x. A different way of writing that exact same equation is using what's called a logarithm. And it's the logarithm, as we're going to find out here in a little bit, is an inverse of this function here. But we can't just flip-flop the x and the y. That'd be part of it, but let me show you. So the way you write a logarithm, the way you take this exponential function and you write the inverse, you write the logarithm, is like this. Oh, sorry, no, that's just an example. 8 equals 2 to the third power. 2 times 2 times 2 is 8. All right, this is how you write a logarithm. So we abbreviate logarithm with log. If you look on your calculator, you'll probably see a button that says log. So the way this is written is the base of the exponent becomes the base of the logarithm. And then just like with the inverse functions, we flip-flop the domain and the range. So the domain was x here, the domain here is y. The range was y here, the range now is x. So we take the base of the exponent, that becomes the base of the logarithm. And then we take the domain and the range, the x and the y, and we flip-flop them. Using this example here, 2 to the third power equals 8. 2 is the base of the exponent, so it will become the base of the logarithm. And the 8 and the 3, the domain and the range, we're going to flip-flop. It would look like this. Log base 2 of 8 equals 3. And that's true. Both of these are true statements. And we'll expand or we'll explore, how to use this here too. But that's the basic idea. That's how we write a logarithm, is we take an exponential function and we can write it as a logarithm. And vice versa. If we have a logarithm that we're given, we can take the base of the logarithm and make it the base of an exponent, and we can switch the domain and range. 2 to the third equals 8. This will get more familiar as we do more problems. You'll get more comfortable with it. Here's another example. 10 to the second power equals 100. 10 squared equals 100. If we wanted to rewrite this as a logarithm, the base of the exponent is 10. So the base of the logarithm will be 10. And we flip-flop the domain and the range. So that's the idea. Little bit of history. I'm not going to spend a lot of time on the history of this. Logarithms were originally developed a long time ago. And they were developed BC, before calculators. So without calculators, if you wanted to multiply really big numbers together, that's very tedious. Adding big numbers together isn't so bad. You line up the ones place, the tens place, hundreds, and you just start adding. Multiplying big numbers together is tedious. I'm talking like 5-digit number times a 5-digit number. If you go ahead and do that, it just takes a long time. There's lots of places for mistakes. This is where people in college or in high school even would turn to their book of logarithms and trigonometric tables. Remember, this is before calculators. You can't just punch it in your calculator. No phones, at least not that have a calculator in them. And so the way this book is set up and the way you would multiply big numbers, and that's just one thing you could do with logarithms, is you would take a number, big number, and you would convert it to its logarithm. And in this book, it's just a whole bunch of logarithms. I mean, that's it. We got just logarithms and logarithms, and there's a whole bunch of numbers. So you would find your number, and you would find the logarithm of that number, base 10, or base whatever it is. And what you can do with it then, once you have the logarithm of that number and the logarithm of your second number, the two numbers you're multiplying, instead of multiplying those two numbers together, all you have to do is add. And this seems really like I'm confusing you. I probably am. This will make, I'll reference this again in the second video, I think, about properties. But if you convert the two numbers to logarithms, you don't have to multiply them together. All you have to do is add the two logarithms together. And then you look back in your book and you convert it back to a standard number. So it sped up the process, and it allowed for fewer mistakes in your arithmetic. That was one way it was used. That's really not how we're going to use it, because you have a calculator. And so it doesn't fill that void very well anymore. But it can be used for that, and it was very effectively used for that before BC, before calculators. Let's look at some more examples. I'm moving on from the historical end of it. I'll reference it again at some point. But so if we were going to try and solve for x, so you got the log base 3 of x equals 4, the log base something, the log base x of 9 equals 2, and the log base 4 of 64 equals x. If we rearrange these problems into an exponent, so the first one here, the base of the log is 3, which means the base of the exponential function is going to be 3. We're going to flip-flop the x and the 4, and so we'd end up with 3 to the 4th power equals x. Well, then I can solve. 3 times 3 times 3 times 3 is going to be 81. So I can solve that. Look at the next one, same idea. The base of the logarithm is x, so the base of the exponent is x. I flip-flop the 2 and the 9. Some number squared equals 9. I can solve that too. 3 times 3 is 9. Or negative 3 times negative 3 is 9. For this one, same idea. 4 to the x power is going to equal 64. 4 to some power, 4 times something, however many times I have to multiply that 4 is going to give me 64. So the solutions are going to be, should be plus or minus 3. Here are our solutions for that. So that's one way we can utilize being able to go back and forth between logarithms and exponents to solve for different parts of that problem. Calculators. Okay. Calculators, we moved on from history, now we're into calculators. Calculators are great. Get rid of this. Nobody wants to look at those. Calculators, woo-hoo. Okay, one thing that calculators do a wonderful job of is they're very fast at doing what they've been programmed to do. The only problem with that is they're not always programmed to do what we want them to do. Calculators are really good at doing a logarithm. So this is log. On the graphing calculator, there's another logarithm button. That logarithm button is only for base 10. I'm going to say that again. The logarithm button here is only good for base 10. It's called the common log. If I go back here, I said that log base 10 of 100 equals 2. Let's try that. Log, it's automatically base 10. I cannot change that. Of 102. Hey, it worked. However, if I want to do log base 2 of 8 equals 3, I can't use a calculator to do that because your calculator only does log base 10, called the common log. There's one other logarithm that it'll do, and we'll get to that later. But for the most part, log base 10. So calculators are great. They're quick. They're fast. They're very accurate, but they only do so much. And so that's where we need to be able to problem solve, and we need to be able to find ways to utilize the calculator and still answer our question, even if it's not programmed to do exactly what we want. And so that's what we'll be kind of practicing, is how to utilize the calculator to get the answer, even if it's not exactly right. One thing that'll help us, so you do not need to write this down if you don't want, but if you look at these two graphs, We've got f of x equals 2 to the x power. We've got this exponential function. And we have this logarithmic function, f of x equals log base 2 of x. These two graphed lines appear to be a reflection across this line y equals x. And if you recall, if two functions are a reflection across this diagonal line here, they must be inverses of each other. And that's true here. An exponential function and a logarithmic function are inverses of each other. That's another tool that we can use to help us solve problems. I'm going to show you what I mean. And you might not like this at first, but you'll get accustomed to it. I guess I'll give you another example first before I show it to you with the logarithms. Here's an example of a problem. If we have this function, 3x minus 2, and we've already gone over how to find the inverse function for that function. So these are inverses of each other. If we take the function at 2, so plug 2 in, 3 times 2 is 6, minus 2 is 4. So we can find that. That's not so bad. If we find the inverse function at 2, 2 plus 2 is 4, divided by 3, 4/3. Now let's do some compound functions here. If I take the inverse function of 2 first, 4/3, and I take that 4/3 and I plug it into the original function f. Okay, so 4/3 goes in here for x. 3 times 4/3 is 4, minus 2 is 2. I just got the number 2 back out again. If I do the same thing here, if I take the function at 2, so the function at 2 is 4, and I plug that into the inverse function. So I take 4 and I plug it in here. 4 plus 2 is 6, divided by 3 is 2 again. If you take the function of its inverse, you get the number back. It's like they cancel each other out. Or if you take the inverse of the function, it's like they cancel each other out. You just get that number back again. It's like adding and subtracting our inverse operations, multiplying and dividing our inverse operations, squared and square root. You get the idea. These undo each other, and we just get that number back again. For logarithms, it works the same way. A logarithm and an exponential function are inverse functions. So if I have log base 10 of x equals 3, which that we could probably figure out, I think we already did figure that out by rearranging it. Another way that we could solve that is to say, well, I know that the logarithm is the inverse of an exponential function. So if I take 10 to the power of log base 10 of x, I have to do the same thing to both sides, so 10 to the power of 3. This 10 to the power of log base 10 here, this piece right here that I'm circling with my arrow, these are inverse functions. They more or less cancel each other off. And we just get x back out. And 10 to the third power is 1,000. So a faster way to do this, rather than just rearranging it and figuring out the answer from there, is we could just take the inverse. We could take 10 to the power of both sides and get that value here. That might seem like a more complicated way than is necessary, but sometimes we don't know what the answer is. So let's take this example, 10 to the power of x equals 54. I know 10 to the 1 power is 10. I know 10 to the 2 power is 100. 54 is somewhere in between, some decimal. I have no idea what it is. To solve for x, to figure out what that is, rather than guessing and checking and trying to get as close as possible to 54, a more efficient and more accurate way of doing it is to say, well, I know that an exponential function, 10 to the power of x, is the inverse of a logarithm. So if I take the logarithm of both sides, log base 10 of 10 to the power of x, this log base 10 and 10 to the power are inverse functions, just like it was over here on the left. So these are inverse functions. Log base 10 of 10 to the something is just going to give me x back out again. And log base 10 of 54 is just some number. And I can type that in my calculator. That I can plug into a calculator and go log 54 equals decimal. Got it. Generally speaking, this is what we're saying. That if you take a base to the log, to the power of log base b, whatever, as long as these match b and b, we just get x back out again. It's like they cancel each other away. And if I have a exponential base here, b to the x, if I take the log base b of this power, as long as these two bases match, it's like they cancel each other off. And we just get x back out again. That's going to come up when we start talking about compound interest again. And we're going to use that fact to help us with compound interest too. Okay, I'm going to stop here. I think I've thoroughly exhausted this amount of time. You'll get some practice. You'll get lots of practice. Please email me if you're completely lost on how to go back and forth between logarithms. But we'll keep practicing it.